Um, so first talk is about BeePL, Correct-by-compilation kernel extensions by Swarn. Priya. Go.
Thank you, Anita, for the introduction. Hello, everyone. Today I'm going to talk about BeePL. It is a collaborative work with all these amazing people listed on the slide. Before diving into the motivation of why we are doing it, let's do some background details. So I'm going to talk about what is eBPF. I'm sure some of you might be familiar with it. So eBPF is a Linux technology which helps us to enhance the capability of kernel without doing low-level kernel programming or writing kernel modules. So basically from the user space, we can track low-level kernel applications, we can track information about the packets arriving on the network, we can detect malware and so on. So I would like to discuss about how this eBPF ecosystem works. So we write an eBPF program. So when it all started, people used to write this in C, but with the evolving research, there are existing languages that are also used to write eBPF program, for example, Rust. There are also languages like Go, Lua, which can be used to write user space code and which can help in loading the eBPF program in the kernel. And then there exists a compiler which transforms this eBPF program to BPF bytecode. And on this BPF bytecode, there is a verifier. As we all know that kernel is a critical part of the operating system, so verifier checks for various safety properties. For example, it checks for type safety, it checks for termination, it checks for stack uses. For example, an eBPF program has a bounded stack limit of 512 bytes. So the verifier checks for it, and then absence of undefined behavior, some security issues, and not the least, which is the memory safety, for example, dereferencing a null pointer, out of bound access, and so on. Once the verifier gives a check that the BPF bytecode is safe to load in the kernel, and then this verified BPF bytecode is JIT compiled to produce the machine specific code. Now, as we see that verifier plays a crucial role in this whole eBPF ecosystem. Verifier is built using abstract interpretation technique, which is a static analysis technique, and the verifier aims to do the verification which is sound. That means it does not allow the unsafe program to be loaded in the kernel. But as we all are aware of the fact that writing correct static analysis is hard, so there are various CVEs that has been reported in past which is related to the bug in this eBPF verifier. Now the second problem statement that I want to discuss is that though people use a strongly typed language like Rust to write this eBPF program, but even their strong type system is not enough to reason about all the eBPF properties. So this is a table which compares C and Rust. This table is a bit controversial because in last session we saw a lot of talk related to how Rust can go wrong. So let's focus on some of them. For example, for type safety, we know that C provides type safety to some level, but it also has, for example, implicit cast, it supports void star. So we cannot say that C language can be put in the category of type safe language for this eBPF ecosystem. But for Rust, I have put a tick mark there because Rust is known to have a strong type system. Another property is termination. As we all know that neither C nor Rust can reason about termination at compile time. For stack uses, so the circle represents partial reasoning about these property at compile time. For example, for Rust, because it has a strong type system, it can avoid situation like buffer overflow. But if we want to reason about property like bounded stack space, whether Rust can reason about it or not, it's still questionable. Another property is memory safety. C is not known to be a memory safe language, but because of the Rust ownership, lifetime, and borrowing all these features, we can say that Rust is a memory safe language. And then in the eBPF ecosystem, there are a bunch of helper functions which are checked by the verifier, but those are the basic type checks. So Rust provides some kind of wrapper around them so that the user cannot do pointer arithmetic at the Rust level. Like, it provides more safety for the helper functions as compared to C, but not fully. And then absence of undefined behavior, we can say that Rust does better than C. In terms of, there are also possibility of transient execution attacks in the eBPF program. And for both of them, I had put the partial check because in terms of C, at the LLVM IR, we can still provide some mitigations against transient execution attack. And in terms of certified compilation, we know that there exists a formally verified compiler for C, which is ComCert, but ComCert does not produce BPF bytecode. So for that reason, we have a partial support there, and Rust does not have a certified compilation. Now the problem is, even if the language like Rust has a strong type system, but the compiler is not formally verified to preserve those properties till the BPF bytecode. So even if we use Rust, we compile it, we produce the bytecode, but at the bytecode level, we need to use the verifier again, and the verifier has these shortcomings like it has false positive, it has state explosion issues, and so on. So this is a simple program. It does not represent a real bug in the verifier, but it is kind of a limitation in the eBPF verifier. If we see the line 11 and 12, it has a for loop, and that for loop starts from 0 and goes till h proto. If we look in line 7, we know that the type of h proto is unsigned 16. So we can, by looking at the program, we can see that this program will terminate because it will go from 0 to 65535, like 2 to the power 16. But the verifier ran out of space, and it was not able to allow this program to be safely loaded in the kernel, because the verifier has a limit of 1 million instructions. So our approach is, we want to design a language which we call BeePL. We want to design a strong type system which can reason about maximum number of eBPF properties at the source level. And then we are interested in writing a BeePL compiler which takes the BeePL and produces ComCert source. And from there, we are interested to use the ComCert compiler to produce a BPF bytecode. And we want to formally verify all the part of our approach using the theorem prover calc. So as this project is in early stage, we took inspirations from all the existing languages and their type system. For example, the first is the effect system. We all are aware of the basic abstract type system which captures the type of the input and the output of the function, but they don't capture the effects that a function can produce. But there is a language called Coca, where Coca type system can capture effects like divergence, exceptions, and the effects related to state. For example, there are two programs. The left program is written in Rust. So there is a while loop which does a check on R, whether R is equal to 5 or not, and then it prints something. Now when this compute function is called on the number 6, we know that this will not terminate, and the Rust compiler did not give us a warning because for sure Rust does not reason about termination. But the same program written in Coca, we could see that the effect is, it produces two effects, console and diff, where console means because it is printing something, so it produces console, and divergence because the type system can detect that this program will not terminate. Another type system that we are interested to incorporate in our language is called substructural type system. So here is a simple example. So we have an abstract type called file, and there are various operations that are being done on this abstract type file, for example, open, read, etc. But looking at the type of these functions, we are not able to predict, or we are not able to infer that if we are trying to close a file that was already closed. So in that sense, we are trying to use substructural type system which captures the number and order of the use of data structures. So using the substructural type system, we can avoid the situations where we are trying to do operations on the object which are on the invalid state. And Rust for sure uses this substructural type system in its memory management, for example, linear type system, affine type system, and so on. So here is just a simple introduction to substructural type system. So apart from the basic type int, float, or char, we'll also have quantifiers. For example, there are linear and unrestricted quantifiers. So what does linear quantifier say? It says that a variable should be used exactly once. unrestricted says that we don't have any restrictions on how many times a resource is being used in the program. So if we look at the typing rule, so we have an initial typing environment, we have a term T. So in the typing environment, term T produces the type T and also the leftover typing context, which can be used to type check rest of the program. So in terms of unrestricted variable, we see that the rest of the typing context still have this variable x, because x can be also used later on in the program. But when we say that the type of variable x is linear, we see that the left of the context that we have to check the rest of the program does not have that variable. So that variable is safe to deallocate after its single use. Next is the refinement type system, because a well-typed program can also go wrong. For example, if we do division by 0, integer overflow, and so on. So for this purpose, we want to also incorporate refinement type system in our language. So basically, a type system, like for now, we have in mind that it will be a combination of effect type system, substructural type system, and refinement type system. Now, once we design the type system, how do we know that whether our type system is correct? So we have the plan to formally verify the soundness of the type system. So we'll do the machine check proof using the theorem prover Coq. So this theorem is still on paper. It might evolve later on. So what it says is that if in our typing context, a program P produces a quantifier Q type tau and an effect eta, and we check that this effect does not contain divergence, panic, stack is in bound, then you can say that the program is eBPF safe. Now the question arises that if we have the source program which is eBPF safe, can we also say that the bytecode that we get after compilation is also eBPF safe? We cannot guarantee this because compiler optimization might break this property. So for this purpose, we have we are planning to design a formally verified compiler, but before preservation, we need to prove the functional correctness of the compiler, because if the compiler is not functionally correct, we cannot prove anything about preservation. So for ComCert part, ComCert is already proved to be functionally correct, but because we have to extend ComCert to produce a BeePF bytecode, so we also need to extend the functional correctness in that part. But for the BeePL compiler, we need to write the proof in Coq, which can be shown using this theorem, which says that if we have a BeePL program PB, which starts from an initial state SB, it produces a final state SB prime, and this BeePL compiler compiles this BeePL program and produces the ComCert program PC, and the execution of PC produces the final state SC prime, then we are interested to prove that the final state of the BeePL program and the final state of the ComCert program are in some kind of equivalence relation. Now, after we have proved the functional correctness, we are interested to prove the preservation of properties till the BeePF bytecode. So the first part is proving for the BeePL compiler. So if our source program is eBPF safe, which will be guaranteed using our type system, and when we compile it and the compiler says that yeah, it is a success and it produces the C program, then the C program should be also eBPF safe. Similarly, we also prove this same theorem for the ComCert compilers. So if the source program is eBPF safe and we compile it using ComCert compiler and produces the BeePF bytecode, then the BeePF bytecode is also eBPF safe. So all this proof will be formally verified using the theorem prover Coq. So that's all I have for today, and I'm open for any questions.
Thank you. Thanks for the talk. And the floor is open for questions.
Hello, thanks for the talk. I'm not entirely sure I understood what exactly your notion of eBPF safe is that you will get out in the end in the formal statement out of your program. Is this the program passes the particular checker implemented in the kernel, or is it the program has the properties that we need it to have for safe execution?
So those properties needs to be checked by the type system, and those properties are basically what is listed here.
Yeah, but do you prove that the final BPF program has those properties?
Yes.
Or do you prove that the final BPF program will pass the kernel verifier? Because the kernel verifier is naturally incomplete.
So our end goal is to bypass the verifier. Like our end goal is that the whole tool chain will come with the type system and formally verified compiler. Whatever it produces can be loaded safely in the kernel. So end goal is to bypass the verifier. And
Okay, so practically how is this meant to work? Like the kernel can't trust user space. So does this entire toolchain run in the kernel somehow, or like I'm not quite sure.
So at the end, we are planning to have some kind of certificates which will ensure that the program, the bytecode is coming through our certified toolchain. I'm not sure at this moment how it will work at the end with respect to Linux community, but yeah, but like some kind of certification we will have, which will check whether the program is coming through our toolchain or not.
Okay, so there's supposed to be like a standalone certificate that you can easily check and like, okay, that makes sense, thanks.
Thanks. Can you clarify a little the role of CompCert here? Because you show it producing bytecode as the output, which it normally doesn't.
So our language is a functional style language, which is BeePL. So the BeePL will get compiled to CompCert source. And then CompCert compiler will be used to transform that CompCert source to produce the BeePF bytecode. So basically the compiler consists of two components. One is the BeePL compiler, and the rest of the part is the CompCert compiler, which produces the BeePF bytecode at the end.
But it doesn't ordinarily.
Yeah, we have to extend the compiler to produce the BeePF bytecode.
Oh, okay.
Yeah.
Do you get from CompCert that all these properties are preserved? Like, I mean, also the security vulnerabilities? Like,
so that is a very good question, and it is very hard problem to solve for CompCert, because right now CompCert only preserve constant time property. It does not preserve speculative constant time property. But I am hoping that there are two, like at least one paper in POPL which will give us some direction, though it is related to Jasmine, which has more information like what variable goes to stack, what variable goes to register. But in CompCert, we don't have all these information. So it will be hard to preserve speculative constant time, but we hope that we will come up with some solution in terms of.
but the other properties are all included.
I mean, for that basic CompCert, preserve termination, undefined behavior, like absence of undefined behavior, all these things. For stack uses, there is an extension of CompCert, like if we provide an over approximation at the source level, then CompCert preserves that it does not break it. Like it can be reduced, but it won't go beyond it. So yeah, rest are doable except the speculative constant type preservation.
I actually have two questions. So one, how did you come up with this list of properties? Is there a common agreement, some sort, that these are the highly desired properties?
I would say just by reading the existing framework that deals with eBPF, for example, Rust framework like Aya, Cilium, or the actual eBPF verifier code. So they have like blog posts and papers. So
I see.
Yeah.
I see. And then where do isolation properties come in picture from here?
I don't think we are taking into account isolation for now.
Oh, okay. So because one of the main features is the sandbox nature. So I'm wondering how the type system actually enforces that.
Yeah, so I don't think we have looked into isolation for now.
Okay.
So like first we are focusing on these list of properties, and then maybe we look for more properties. Yeah.
Okay. Do I see a hand raised? Or Well, if none, we can thank the speaker. Thank you.